Assalamualaikum wabarakatuh, and good evening to everyone. So we're gonna continue from our last lecture. So from our last lecture, we already cover symmetric encryption of the DES data encryption standard and AES advanced encryption standard. So DES use a 5 style and AES also use a 5 style mode, but more efficient way with a more key length. Okay. So now we go for the cipher blocks mode of operation. So a symmetric block cipher processes one block data at a time. So let's say we have a long, really long message, like you want to send email. Hello, my name is Saidal. My name is John. I am 20 years old. I like to eat cakes, blah, 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 and the whole lot message. So this is a very long message. So you have to break it into a number of blocks. Okay, you have to make it into number of blocks. So in the case of DS and 3DS, the block length is b64 bits. Okay, so every the longer message, maybe you have to my name is John, one block. Let's say my name is John, 64 bits, so that one block. I live in Kuala Lumpur. There is another one block. Okay, so for AS the block length is B128. AS use a longer key length, so the number of block length is B is equal to 128 bits. For longer amounts of plain text, it is necessary to break the plain text to B bit blocks. So you have if you take AES, so you will break it into 1 to 8 bits, 1 to 8. So this 1 and 2 and until n. So let's say like the last one is not in it's not really 1 to 8 bits, maybe it's 100 bits, so you have to add a padding or dummy character, add another 28 more, so it become 1 to 8 bits. Right. So there actually are 5 modes of operation that is been defined by the NIST, National Institute of Standard. So intended to cover virtually all of the possible applications of encryption for which a block cipher could be used. Okay, basically these 5 modes operation covers the advantage and disadvantage, and they analyze. They already like doing a depth analysis. What is the advantage and disadvantage using all these 5 modes? Intended for use with any symmetric block cipher, including triple DS and AES. So all DS, AES, even the stream cipher also can use these cipher block modes of operation. So the first one, the basic one, is the electronic code block mode ECB. So plain text is handled B bits at a time, and each block of plain text is encrypted using the same key. So you use the same key, one key for all, same key. So of course, this if like this is DS, this is DS, it will go into normal DS operation or ES normal operation. So we can cipher text. It will be like this one is my name is John. So one block. I live in KL. One block. I like to watch movies. So this is another block. Let's say this is like 1 to 8, 1 to 8, and 1 to 8, and so on. So it will process all this according to the block. So the term code book is used because for a given key there is a unique cipher text for every bit block of plain text. So C1 is unique, C2 is unique. So C1 only unique for block number 1, C2 is unique for only block number 2, and until Cn is only unique for block number n. One can imagine a gigantic code book in which there is an entry for every possible B-bit plain text pattern showing its corresponding cipher text. So if like the message is long or the data is longer, so you break it into 1 to 8 bits. It's a gigantic code book. Okay. With ECB, if the same B-bit block of plain text appears more than once in a message, it always produces the same cipher text. Okay, let's say my name is John. I live in KL. Okay, let's say I like to watch. Uh, let's say my name is John. I live in KL. I like to watch. I live. And then let's say another block. I live with my mom, something like that. So I live here and I live here. Let's say this is CN plus one block. Will produce the same ciphertext. Okay, will produce I live will produce the same ciphertext. Why? Because you use the same key and you have a pattern here. I live and I live the same pattern. Maybe in KL and with my mom is not the same, but I live actually is the same. I live for block number 2 and block CN plus 1 will produce the same ciphertext. Let's say this is 64. So the first 64 bits of block number 2 and the first 64 bits of block number CN plus 1 will ciphertext will be the same one. Okay, using the same key, and using the same plain text. Sorry. With ECB, if the same B bit block of the plaintext appears more than once, the message always produces the same ciphertext. So we will recover that. Because of this, for lengthy messages, the ECB mode may not be secure. Okay, maybe in a way you repeated that. Okay, you repeated some. If you have a pattern data, you have a pattern, it will be repeated. So the crypt analysts or the hackers can analyze that, and they might realize this is same pattern, and this same pattern will produce the same ciphertext. Maybe they can break the key. If the message is highly structured, it may be possible for criminals to exploit this irregularity. So highly structured means that it has a repeatable pattern. Okay, my name is John, live in KL. I like to watch a movie. I live with my mom, and then my name is Sarah. I live in Kedah. I like to fish. I like to go fishing, and I live with my parents. And then the third one is my name is Chong Wee. I live in Penang. I like to I like to travel, and I live with my wife and something like that. So it's a repeatable pattern. It's highly structured. So the crypt analysts, if they realize this, they might break or retrieve the key. Okay, so this is the problem with the electronic code book mode, using the same key, and all the ciphertexts are unique to that block. So we have a cipher block chaining or CBC mode. Chain means that, okay, the output of the block number 1 will become the input for block number 2 and so on. So in cipher block chaining mode, the input to the encryption algorithm is the XOR. Okay, the input of the encryption is the XOR of the current plain text block and also a ciphertext. Okay, for the first block, you have an initialization vector. Okay, this acts as a C0 or something, ciphertext 0 initial vector. And then the ciphertext for the first block C1 will become the input for the next ciphertext for the next block when you XOR with the next plain text or P2. Okay, the same key is used for each block. Okay, same with the electronic code book mode. The same key is used for each block. It is chained together. This is the chain. This one is chain. Cipher block chaining mode. The input to the encryption function for each plain text block bears no fixed relationship to the plain text block. Okay, the input to the encryption function for each plain text block bears no fixed relationship to the plain text block. Okay, the input and the input and the plain text has no relationship whatsoever. It's really, you can see it's a random. For decryption, each cipher block is passed through a decryption algorithm. This is one is for the decryption. Each cipher block is passed through the decryption algorithm. The result is XOR with the preceding ciphertext. So you have a ciphertext here. Okay, the first one always use initialization vector, the same one, and then ciphertext for block one will use as input for block number two, XOR with the decryption function. Okay, so you can basically you can write a ciphertext here. Cj is equal to encryption function of k with the k and the Cj with the Cj minus 1 XOR with Pj. Okay, so you have here Cj, the ciphertext of the current, let's say C2. Okay, you have C2 here is equal to encryption function of K with the input of C1 XOR with plain text number 2. So this is the ciphertext function. This is ciphertext function. Okay. And then for the decryption function, you have here decryption of, okay, decryption. Look at this decryption for input K and input ciphertext. So you put your K, CJ, sorry. So we have here decryption function of K and CJ, let's say it's a CJ, is equal to decryption of K, encryption of K and CJ minus 1 XOR with PJ. Okay, so this is the decryption function. Alright, so if you look at this, the E is the CJ. It's a CJ. This is the encryption function. So you can simplify it, become D KC is equal to CJ minus 1 XOR with PJ. Okay, D, the encryption function of K and CJ, CJ minus 1, decryption function CJ minus 1, and times with the XOR with the PJ. Okay, so this is the cipher block chaining mode. So one of it is the initialization vector must be known to both sender and receiver. IV, sender and receiver must know. Okay, and IV also is like similar like key, and it must be protected so that others cannot know the IV as well, and the key. Okay, one reason for protecting the IV is if an opponent is able to fool the receiver into using different value of IV. So let's say like the hackers, they try to fool a receiver into using different value of IV, then the opponent is able to invert selected bits in the first block of plain text. Invert the selected bits in the first block of plain text, and if he do a more analysis, depth analysis, maybe he can crack the key. Okay, so this is the cipher block chaining mode. Okay, now we go to the third one, which is cipher feedback mode. All right, so it is possible to convert any block cipher into a stream cipher by using the cipher feedback or CFB mode. Okay, cipher feedback mode. So it also can operate in real time. Let's say if a character stream is being transmitted, each character can be encrypted and transmitted immediately using a character-oriented stream cipher. Okay. Okay. In this figure, it is assumed that the unit of transmission is S bits. Okay, S bits. This one is S bits. A common value S is 8, so we 8 bits common value. Okay. as with CBC, the units of plain text are chained together. So same like the second method, the CBC, which is cipher block chaining mode. The units of plain text are chained together, alright? So that the cipher text of any plain text unit is a function of the preceding plain text. So this one, same like the previous method, this cipher text will become the next input for the next block. So for the encryption, the input to the encryption function is a B bit shift. Is a B bit shift. Okay, is a B bit shift register that initially set to some initialization vector. Okay, same like the first one. The first block you use the initialization vector. Okay, both sender and receiver must protect this together with the key. The leftmost or most significant S bits, the leftmost, this one, this part of the output of the encryption function are XOR with the first unit of plain text P1. So this part is XOR with the first unit of plain text P1 to produce the first unit of ciphertext C1. So you XOR this with the plain text P1, you get this ciphertext. But before that, you encrypt the initialization vector and the key. Then you the shift register, the output will be a shift register where you select the leftmost bits, S bits, 8 bits, and you XOR with the P1. Okay, first unit of plain text P1 to produce a ciphertext. So this ciphertext C1 is then transmitted into the next block. Okay. For decryption, the same scheme is used except the received ciphertext unit is XOR with the output of the encryption function. So the first ciphertext, the received ciphertext unit is XOR together with the encryption function to produce the plain text unit. So you XOR the C1 with the encryption function, and then you get the P1, the plain text number 1. Okay. So you have here like C1. If we try to write down the equation, C1 is equal to P1, plain text 1, you XOR with the S bits of encryption function of K and initialization vector. Okay, this is the C1. And for the P1 here, you have a C1, you XOR with the S bits of encryption function of this one, E K I V. Okay. Okay. This is a S bit cipher feedback mode. It's similar with the what we call that cipher block chaining mode, but you have to select the S bits and XOR with the plain text or XOR with the ciphertext. Okay. Now we go to the last one, the counter mode. So you have your counter mode. Remember the electronic code boot mode. So you have here counter 1, encrypt, same like electronic code boot mode. Counter 2, encrypt, counter n, and encrypt. But the difference is you have here, this one is just using for the electronic code boot mode. It only use the plain text, but here in the counter mode we use a counter 1, you encryption function of counter 1 and K. Counter 1 you can see is a seed, is a pseudo-random seed. Okay, and then you do the encryption function, and this encryption output you XOR with the P1. Okay, a counter equal to the plain text block size is, so this counter is equal to the plain text block size. Okay, So typically the counter is initialized to some value and then incremented by 1. So this one counter 2 incremented by 1 until counter n. So where you have a module, this the 2 to the power of b, where b is the block size. Okay, block size. For encryption, the counter is encrypted, then XOR with the plain text block. So the encryption function counted and then XOR with the plain text block to produce the ciphertext block. So this, it is not a chain, okay? It's not a chain. So it is unique, but you have a counter. This counter is different value, the seed number. For decryption, the same sequence of counter value is used. Okay. For the same sequence number counter is used, which encrypted counter XOR with the ciphertext block. So this one XOR with the ciphertext block, the encryption function or decryption function. Actually, this is a decrypt. Okay, and then you have a C1. You XOR with the encryption. This is actually a encryption function, and then you XOR with the C1, and then you have a P1. You can retrieve back the your plain text. Okay. So counter mode is now actively used in the what we call it cipher blocks modes of operation. So the advantage like hardware efficiency, unlike the chaining modes, encryption. So if you see the chaining modes of CBC and what we call that cipher feedback mode, you can see that counter mode can be done in parallel on multiple blocks of plain text or ciphertext. So for the chaining modes, the algorithm must complete the computation on one block before beginning on the next block. So in the chaining mode, you have in the chaining mode. So this the block you have to complete all the equation here, complete the process. Then this one will become the input for the next block and so on. So this limits the maximum throughput of the algorithm. In counter mode, the throughput is only limited by the amount of parallelism. So in today's world of CPU with multi-core and multiple CPU in one machine, counter mode is the best, is the best method for the cipher blocks modes of operation. Software efficiency, similarly, because of the opportunities for parallel execution. So you just not only just hardware, software also you can use parallel features. If you learn parallel programming, you can there's a term called aggressive pipelining, multiple instruction dispatch per clock cycle, a large number of register or single input, multiple data instruction. So there's the software efficiency plus the hardware efficiency of parallelism. The counter mode is the best. Okay, then you have a pre-processing where execution of underlying encryption algorithm does not depend on the input of the plain text or ciphertext. So the counter mode doesn't depends on the plain text or the ciphertext. Okay, and then you have a random access. It's a random for the counter, the seed number counter. Uh, And then the counter mode also is really secure the electronic code book mode and secure same as the what you call that, a cipher block chaining mode and the cipher feedback mode. And also it's a simplicity. Unlike the ECB and CBC modes, counter mode requires only the implementation of encryption algorithm and not the decryption algorithm. So you can see here is the encryption and this is the encryption, both encryption algorithm. This matter most when the decryption algorithm differs substantially from the encryption algorithm, as does for AES. So in addition, the decryption key scheduling need not to be implemented. So this is the cipher block chaining modes. Okay, you have the hardware efficiency, software efficiency, pre-processing, random access, provable security, and the simplicity. Okay, now we go to the random and pseudo-random numbers. There's a number of network security algorithms based on cryptography that make use of random numbers. Okay, random numbers is widely used in the cryptographies, or we call that not really a random numbers, because they have a mathematical distribution that it has some pattern, but it's really difficult for the man, even a computer, to calculate or to predict what is the next random numbers. What is the next random numbers will appear. So it's examples like generation of keys for the RSA. This is a public key encryption algorithm. Another public key algorithms, which in the next lecture. So the generation of symmetric key for use of temporary session key. So you can also generate a symmetric key, a temporary session key used in that particular session or period. It is used in a number of networking applications such as transport layer security, Wi-Fi, email, and IP security. In a number of key distribution scenarios such as Kerberos, a key distribution scenario, random numbers are used for handshaking to prevent replay attacks. So there are two main distinct principles of the random numbers, which is the randomness and the unpredictability. So the randomness, the following criteria you use to validate the sequence of numbers. So you have a uniform distribution. The distribution of bits in the sequence should be uniform. Frequency of occurrence of ones and zeros should be approximately the same. This is a uniform distribution. Let's say you have you have 8 bits. Let's say you have 10101010. So they have 4 bits 1 and 4 bits 0. So maybe the next number can become 11001100. Still 4 bits 1, 4 bits 1, 4 bits 0, and then you have 1001, and then 1001, still 4 bits 1 and 4. So this is the uniform distribution. Then you have the independence. No one subsequence in the sequence can be inferred from the others. So no one subsequence keys or subsequence we call that digital generation can be inferred from others, totally independent. So the next, meaning that the next output does not really depends on the previous input, previous output. The next, okay, like block number 2 does not necessarily depends on the block number 1. You can see that on the counter mode. There is no test to prove independence. So okay, you can apply a number of statistical model in order to test the strength of independence. Of course, this is not really, because it's a mathematical, it's not really random. It's called a pseudo-random, just like a pseudoscience. It's not a real science. The pseudo-random is not a really random numbers, but it looks like a random numbers. So this is the concept you have to know, because it's mathematical. You can create, maybe they have a pattern or something, but it's really difficult. It's really difficult to crack that. The general strategy is to apply a number of tests until the confidence that independence exists is sufficiently strong. There's no independent test, but you can apply a number of tests, well-known tests, until the statistical confidence of that independence random numbers is sufficiently strong. Meaning that it's strong, it's really strong. The independence level is really strong. It's not really independence, but the independence level is really strong. Okay, it's not really a random but pseudo-random numbers, but it really difficult to predict. Difficult to predict the next sequence of output. So in the unpredictability, so in practice such as reciprocal authentication or 1 over the X, and session key generation, the requirement is not so much the sequence of number be statistically random, but the successive members of the sequence are unpredictable. Okay, it means that it's not repeatable, meaning that okay, let's say you have a let's say 1 2 3 4, then you have a 3 1 2 4 4 1 2 3, and so on, meaning that if like more numbers or more bits, it much more it is very difficult to create the randomness. Okay, it's like this is one the random unpredictable. Successive members of the sequence are unpredictable. Who knows that after 1 2 3 4 is 3 1 2 4? Who knows that? You can never know. All right. With true random sequences, each number is statically independent of other numbers in the sequence and therefore unpredictable. through random sequence, each number is statistically independent of other numbers in the sequence. So it does not depend on the next numbers or the previous numbers. Care must be taken that an opponent not be able to predict future elements of the sequence on the basis of earlier elements. So whatever system cryptography you want to use, or the good system that being built is, like hackers, they cannot predict the future elements just solely basis on the previous inputs or earlier elements. They cannot predict what comes, what is the next plain text given the cipher text of the previous elements or previous blocks. This is unpredictability. So you have here what we call that a random and pseudo-random number generators. You have here basically is a three random pseudo number generators. Okay. First, you have a two random number generators. So these two form, you have a two form of pseudo-random number generators. TRNG or true random number generators takes as input a source that is effectively random, source of random. This is totally random. Okay. The source is often referred to entropy source. Entropy source. Meaning that it's really random. Two random number generators. In essence, the entropy source is drawn from the. So in essence, the entropy source is taken from the like a keystroke patterns. This electrical activity, mouse movement, and so on. Really random. You cannot predict your mouse movement. Okay. Maybe a system clock or something. The source or combination of sources serve as input to an algorithm that produces random binary output. The TRNG may simply involve conversion of analog source to a binary output. So this true random number generator may also involve additional processing to overcome any bias in the source. Okay, now this is the first one, true random number generators. And we have here the second one, a pseudo-random number generators. So PRNG takes as input a fixed value called a seed. So this seed is a fixed value and produce a sequence of outputs using a deterministic algorithm. So this is why deterministic, you can determine or you can predict what sequence of elements next, the next elements. So this is why I call a pseudo-random number generators. So there is also some feedback path that you can use. And also bit stream is determined solely by the input value or values. Okay, bit stream is solely depends on the input values. And then of course you have a PRF, a pseudo-random function. So used to produce a pseudo-random is similar with the PRNG. PRF also takes input a seed plus some context specific values such as user ID. So this one context specific such as user ID or application ID and so on. So they have just like PRNG, but they have another additional inputs. We call that a context specific values. Okay. So in algorithm design to create a random number generators, okay, a random number generators, you have a purpose bit algorithms designed specifically and solely for the purpose of generating pseudo-random bit streams. Okay, so this purpose bit algorithm is solely for the purpose of generating pseudo-random bit streams. Algorithm based on existing cryptography algorithms that have effect on the randomizing output. can serve as the core of pseudorandom number generators. They have three broad categories of cryptography algorithms to use as in the PRNG. We have a symmetric block ciphers that we learned before, asymmetric ciphers, which we will learn in the next lecture, and hash function and message authentication codes, also in the next lectures. Now we go for the stream cipher. Okay, we go for the stream cipher. As you all know, RC4, the stream cipher is another symmetric encryption. Symmetric encryption. It is used. It's similar. You have a key. You have a same key used and something, and then you generate you scramble. There's some permutation and stuff. And then the real world stream cipher, the protocol, we call that the first one is RC4, used in wireless equivalent protocol, wireless network security. So there is also RC4 also used in TLS or HTTP security. Okay, this RC4 is not recommended to use anymore. You can click on this rc4nomore.com. Okay, you can see what's the attack that they have done, that they expose the vulnerability of RC4. And then we have A51 used for encrypting GSM phone data and conversations. So NSA is known to be routinely breaking it. So your GSM phone data conversation, maybe when you converse, I don't know, maybe authority or some that have authority can hear you, that can listen to you, or eavesdropping. In the cryptography world, we call it eavesdropping. So stream cipher design consideration. We have here like the encryption sequence should have a large period. The longer period of repeat, the more difficult it will to do a crypt analysis. The period means like, okay, let's say we have we have a key like, okay, 3 2 1 4 6 7 8, and then it repeat 3 2 1 4 6 7 8. So this is the period number. After 8, it will repeat 3 2 1 4 6 7 8, something like that. The longer the period of repeat, the more difficult it will to do the crypt analysis. So the longer period, meaning that it's very difficult for hackers to break the key. It is usually it's a 10 to the power of 100, the period. Okay, the key stream should elevate the properties of true random number stream as close as possible. The more random appearing the key stream is, the more randomized the cipher text is, making crypt analysis more difficult. Okay, level of, if higher level the higher level of randomness, so it is more secure. Okay, the stream cipher will be more secure. Randomize the cipher text. The higher level of random cipher text, it is very difficult for the hackers to break it. The serial random number generator is conditioned on the value of the input key. It is to guard against brute force attacks. The key needs to be sufficiently long. With current technology, a key length of at least 1 to 8 bits is desirable, as we have seen in the previous table. Previous table, 1 to 8 bits is the minimum for the key. It takes can take a couple of years to break it. All right, with the current technology, with the current computer speed. So here you have a stream cipher diagram. You have a plain text byte stream M. You have the key and you have serial number byte generator, and then you XOR it, and you got the cipher text byte stream. So a cipher byte stream, you XOR with the key, and then you get a plain text byte stream. So let's say you have a key 1 to 8 bits using the RC4. Let's say the key stream stroke, you have a 0010 until this one. And then you have a plain text data PT. You XOR it, you will get something like ciphertext. And if you want to get the cipher, so the ciphertext is actually the key stream XOR with the PT. And then when you want to recover the plain text, you XOR the key stream with the ciphertext and you get the plain text data. Okay. Now we go in details for the, so using XOR with the stream cipher, using XOR for encryption, ciphertext is equal to keystream XOR with the plain text, and for decryption you have keystream XOR with the CT, and you get with the, yeah, you get plain text. So this is the truth table or of XOR, exclusive OR. So plain text 0110 keystream KS. So you have a ciphertext here 1010. So decrypt ciphertext keystream and then plain text. So plain text you have 0. So refer to the truth table 00. The same input will produce 0. Different input will produce 1. So same input produce 0. Different input will produce 1. Same as decrypt. You have a ciphertext here 1010. You XOR with the keystream, you get the original plain text back. Now we go to the RC4 algorithm. A stream cipher designed in 1987 by Ron Rivers for RSA security. Okay, it is variable key size stream cipher with byte-oriented operations. The algorithm is based on the use of random permutation. Okay, random still have like cipher blocks. There's permutation, meaning that bits 1 become bits 8, bit 2 become bits 16, bits 3 become bits 2, and so on. It is used in the secure socket layer, transport layer, or SSL TLS standard that have been defined for communication between web browsers and servers. So RC4 algorithm used in the secure socket layers and SSL, the first version of SSL TLS, and it's also used in the wired equivalent web, okay, protocol, a kind of the first wireless security protocol, and also used in the newer Wi-Fi protected SSL protocol that are part of IEEE 802.11. If you see IEEE 802.1x, it is all wireless, all right, wireless LAN standard. So we go details on that. We will go details on the RC4 algorithm. Okay, so you have here S. So S here, the first one. Wait, I have to open the. I have to open the. Okay, we will go one by one on this figure. RC4 stream ciphers. The way is encrypt and decrypt. It is just as interesting as DS and AES. Okay. So the first one you have here. Okay, the first one you have here. For initialization, you have here initial state of S and T. So the pseudocode is the for I equal to 0 to 255. So you have a S bit is 256 bits. Okay, 256 bits. S we call that an array, an array of S. You have 256 bits for. So this is pseudocode for I equal to 0 to 255. The array of Si is equal to I, and Ti is equal to K I modulo key length. Okay, and GTH key length. Okay, this is I mod key length. So this is the for initial state of S and T. You have here array S and you have here K. You have here key. Okay, let's go for example. Actually this is for I equal to 0 to 255. So you have do Si is equal to I, and then Ti is equal to K I mod keylen. Okay, mod is modulo. Modulo, it will return the remainders. Let's say 5 divided by 4. So 5, 4. Of course, this conventional way. So 5 minus 4 is 1. So 5 modulo 4 is equal to 1. Modulo, it will return the remainders of the division operation. Okay, let's say you have here, okay, I2255, maybe we change to, okay, let's say we have a simplified RC4 that maybe use only, maybe you only use a 4 bits, okay, 4 bits. Let's say you have S here is equal to 0. Sorry. So you have here S0, S1, S2, and S3 is equal to 0, 1, 2, and 3. Let's say you have a key you have only 3 bits, like 2, 3, or 0. Okay, 2, 3, or 0. So what will happen is for the array S, it will have still it have 0, 1, 2, and 3. But for the key, because you have key K I mod key length, so you have here SI is 0, 1, 2, 3. TI mod key length, meaning that you have to fill in the TI is equal to what's the key, 230, 230, and 2, because it mod key length is 4 bits. So you have 230 and 2. You repeat back the first one. So this is the initial state. The initial state you have as 0 to 3 is 0, 1, 2, 3. And then key from 0 to 3 you have 2, 3, 0, and 2. Although the key you have 3 bits, and so sorry, this one key actually become T. Alright, this is the initial state. And then we go for the second state, the initial permutation of S. Okay, initial permutation of S. So you have here J. Okay, the pseudocode is J equal to 0, the initial state. And then for I, 0 to 255, do. What we do is J is equal to J plus Si. Okay, J plus Si plus Ti. Okay, array mod 256. And then you swap Si and Sj. Sorry, you swap Sy and Sj. So Si, Sj. So this is the second pseudocode, initial permutation of S. Let's go back to this one. Okay, you have here, okay, this is the first one, the initial. So this is the initial permutation of S. Permutation of S. Okay, you have here J0, and then for I 0 to 255, or we replace with 4. do j is equal to j plus si, array, not si, array of si plus array of ti, okay, mode 4, and then you swap si and sj. Okay, if you see this one, we have let's say if you want to do this one by one, okay, you have to do this. I give you the example one by one. You have here example one by one. Let's say you have here what we call that, S0, S1, S2, and S3. Okay, you have here. So you have here the initial state 1, 0, 1, 2, 3. Okay, S0, S1, S2, S3 is 0, 1, 2, and 3. And T1 or the key is 230. Is it correct? 2302, yes. 230 and 230 and 2. So you have here, this is I and J. Okay, we want to what? I and J. You have here I and J. So J equal to 0. This is initially 0, 1, 2, 3. So now if for I 0, so let's say I is 0. If I is 0, so J is equal, if for I 0, so J is equal to, J is 0 in these terms. J is 0 plus, say J 0, the previous one, plus Si, S what? S0, S0 plus T 0, Ti, T0, mod 4. So if we solve this 0 plus S0 is 0, T0 is, this one is T0, T1, T2, and T3. So T0 is 2, mod 4. The value of array at T0, mod 4. So you have here 2 mod 4, where you get 2, okay? So J is equal to 2. So you can fill out the I0, J is equal to, this one is initial state. So J is equal to 2. Then what you do, after you calculate J, you swap S I0, S0 with Sj. Si, this one 0, and J, S2. So you have here S0 here and S2. So you swap here 2 and this one becomes 0. This remains the same, 1 and 3. Okay? And then you do that again. You do that again with, now you increment 1. Now you increment I. So now I is equal to 1. So I equal to 1. If I equal to 1, J is equal to J. What is the previous J is 2 plus S1 plus T1. Is that correct? Modulo 4. So 2 plus S1. S1 is 1. S1 here is 1. S1 here is 1 plus T1 here is, T1 here is 3. Mod 4. Modulo 4. 2 plus 1, 3. 3 plus 3, 6. Modulo 4. So what is the 6 modulo 4? It will return 2. J is equal to 2. So you put here J is equal to 2. and then you swap Si S1 with S2. So you swap S1 and S2. So this one 0 here, this one become here, and 1, and this one 2 and 3. So you're done. Just that you can calculate here, this one 2 0, and then again 1 0 2 3, 1 0 2 3, and then for the last I is 3, j is equal to 1, and then you have your 1 3 2 0. So the final S array is 1 3 2 and 0. Okay, this one is the final one, the final S 1 3 2 0. So we done at this stage only. So we already done at this stage. Now we have done at this stage. So this is just the beginning. This is initial permutation of S. Now we go for the string generation. So the string generation, the pseudocode is you initialize first I and j to 0, and then you calculate I is equal to I plus 1 mode 256. Okay, we use mode 4 because we will try to simplify the RC4, okay, instead of 256 bits. If you try to calculate manually, I try to teach you one by one. It's going to take like, I don't know, 1 day 2 days to complete the table. Okay, I and then j, and then j plus si, okay, mode 256, okay, and then you swap Si and Sj. You swap Si and Sj. So you calculate T. After that, you calculate the T. So we continue here. You calculate T equal to Si plus Sj mode 256. You swap first, then you calculate T, and then you calculate key stream. The key stream that we use is equal to St. Okay, is equal to St. This is considered each, like you have a 256 plain text for the first block. Okay, 256 plain text. Now go back to the whiteboard. So this one you have a final Si equal. So 3 is a stream generation. So 3 is a, 3 is a stream generation. Okay. So you have here, this is pseudocode. This is pseudocode is the, you initialize I, j to 0, and then while true or plain text keylang, okay, keylang. So you calculate I is equal to I plus 1 mod 4, because you use 4 bits instead of 25. J is equal to J plus Si mod 4. Then you swap Si, Sj, and then you use T Si plus Sj mode 4, and then the key stream is St. Okay, this is the pseudocode. I think you can see this is pseudocode. All right, a pseudocode. So final, the new Si is 1320. Let's say the plain text is somehow 4 bits. Okay, to simplify, 3 2 1 0. This is the plain text. Okay, this is the plain text. Okay, now you have to do the table here. String generation, you have to do the table here. You have of course we have here S0, S1, the new one, the new array, S2 and S3. And then here, okay. And of course you have a I, you have a J, you have a I prime. I prime is increment I mean, after the operation, what is the next value of I? And J prime, what is the next value of J of the operation? And you have T. And of course you have K here. So you differentiate here. This one you differentiate between the array, other array, okay, S. Here you have 1320, the initial state, okay? The initial state. So while, okay, ij0, so while true, okay? So if first you put here I and j0, okay? While true or less than plain text key length or same. I is I plus 1. So 0 plus 1 is, so here you do a calculation when I0. Okay, I0, I prime, you become a 0 plus 1 mod 4, or 1 mod for whatever less number than mod is equal to 1. Alright? And then you have a J prime. So you put here 1, 1. You have a J prime is equal to 0. J, the current J is 0 plus SI, S1 mod 4. So 0 plus S1 is 3 mod 4. So you see S1 is 3. So 3 mod 4 is J prime is 3 because less than 4. So J prime here is 3. So you swap Si and Sj. So I prime here Si, S1 and S3. So S1 and S3. S1 and S3. So you swap here, this one becomes 0 and this one becomes 3. And this one remains unchanged. So what is the value of T? Is S1 plus SJS3 mod 4. So S1 is 0. So you look at this S1, the current one after swap. This, if you learn programming, this is after, this is operation. The new value is S, the previous value is S3 and S0, but now after swap, you use the new value after the swap. Okay, Si plus S3 is 0 plus 3. 0 plus 3 mod 4. So you know whatever less is 3. So T is equal to 3. And then K is equal to S3, ST. So you have here S3 is 3. So you have here the first key length is 3. Okay, the first one is 3. Of course, you can complete this one as I mentioned. Okay, let's do another one. Number 2, I equal to 1. So now I prime here 1 and J prime. Okay, the I prime and J prime will become the next value of the next calculation, the next sequence. J prime is 3. Okay, if I equal to 1, so the new I prime will become of course 1 plus 1 2 2 mod 4 is 2. Okay, 2 mod 4 is 2. This is I plus 1 current I is 1. Current I is 1. So 1 plus 1, 2, 2. 2 mod 4 is 2. Okay. J prime is equal to J plus, okay, J prime 3 plus S, what? S I prime, the S, the new I, S2 mod 4. So 3 plus S2, the current S2 is 2. So you put here 2 mod 4. So 5 mod 4, when you divide by 5 you divide by 4, you have remainder. J prime is 1. So I prime is 2 and J prime is 1. Okay. Now you swap what? S2 and S1. S2 and S1. So you swap S2 and S1. S2, S1. So this one 2 and this one 0. 2 here and 0 here. So this one remains unchanged. Okay. S2 plus, okay, this one remains unchanged. 1203. And then you have you have to calculate the T. You have to calculate the T is SI plus SJ, meaning S2 plus S1. S2 plus S1, 0 plus 2, 2. 2 mod 4 is equal to 2. So T is 2 here. And K here is S2 equal to, what is S2? Is equal to 0. Equal to 0. Okay. So you have here 3, 0. Then you have here, okay, 3, 0. So if you complete here is 3, 0, 3, 1. I hope that you know how to calculate that. Maybe in assignment I give you a longer length. Maybe you're more confused. Who knows? Okay. Okay, this is the, okay. So you have here K3031. So this is the key stream that we want. The key stream is 3031. The plain text is what? The plain text is 3210. 3210. So now if you want to get the ciphertext, you KS XOR with plain text. So KS is 3031, you convert to a binary number. KS, you convert to binary number is 3 is 10, this one is 00, 1000, this is 10, and this one is 01. Okay, and the plain text is 3, which is 3210. If you convert to binary, 3 is 10, 2 is 0, 2 is 01, 3 is 2, 4, 3 is 2 is 00, 00, 0, 1, 1, 0, and 1, 1, 0, 1, 2, 3. Okay, 0, 1, 2, 3. Sorry, 3 is 1, 1. Okay, even I confused now. 1, 1, and then 0, 1. So 3 is 1, 1, 2 is 1, 0, 1 is 0, 1, and then 0, 0. So you have got the ciphertext. You got the ciphertext, so you remove this, you remove this. So the ciphertext is 1, 0. If XOR 1, 0, 1, 0, different input. So you have 1, 0, 0, same input, 0. 1, 1, same 0, 1, 1, 0. So 0, 0 is 0, 0, 1 is 1. And you have 1, 1, 0, 1, 1, and 0. So you have here 0, 0, 1, 0, 0, 0, 0, 1. So this is ciphertext. If you convert to binary, if you convert to the base 10 numbers is 0, 2, 0, 0, 2, 0, 1. 0201. So if you want to get the plain text back, you key stream KS plus the CT. So KS key stream is 11001101, and the CT is 0010 0010 00 and 01. Sorry. So 11 is 00110111. So this is 31032 3210. So you get the same, you get same plain text back. So this is 3210. So yes, this the end of lecture for symmetric encryption, lecture 2, which is divided into days. It's very interesting to teach you this. Okay. All the programming language have all this built-in library for all this conventional cryptography. Okay, so this is a summary you can read. So thank you very much.